So this is problems which are related with the AM wave, and this AM will come into the module 1, amplitude modulation. And again, the types of amplitude modulation, so whatever may be DSB, SSB, all are come in this module 1. So module 1 is covered by course outcome 1. That is the first course outcome of this course. So totally this course having 6 outcomes, 6 course outcomes. So this is the first course outcome, and the first course outcome which deals with the outline the basic concepts of communication system, need of modulation, and fundamental elements to realize amplitude modulation systems. So in the previous session we covered modulation index and percentage modulation index, and powers, that is total power, carrier power, and some standard equation which is used to find these values from the given problems. Okay, so the remaining types of problems which is going to deal with this session. Okay, so now we go to start the session. So this is what we are going to deal with another type of problems. So in this problem, a bandwidth of 20 megahertz is to be considered for the transmission of AM signals. So here we go to transmit the AM signals, amplitude modulation signals, by using a bandwidth of 20 megahertz. So if the highest audio frequency is used to modulate, the carriers are not to exceed 3 kHz. So how many stations could broadcast within this band simultaneously without interfering with one another? So already we know that AM bandwidth is less when compared with the FM signal. So here the maximum bandwidth given as 20 megahertz. Okay, so by that problem, first we write the given data. So what the given? The total bandwidth is 20 megahertz and maximum FM, this is frequency, is 3 kilohertz. So the maximum bandwidth of each AMC station is determined the maximum frequency of the modulating signal. Okay, so the station bandwidth is equal to 2 FM max. 2 FM max. So 2 into FM max. So what is the FM max given? 3 kHz. Maximum given 3 kHz. So 3 into 10 power 3. So 3 kHz into this 2. So totally the station bandwidth is 6 kHz. And what another one? Without interfering. So our problem is how many stations that can broadcast simultaneously without interfering. So they given 20 megahertz. So the 20 megahertz, 20 into 10 power 6 divided by 6 kilo. So 6 into 10 cube. So these are the stations. By solving this 20 mega divided by 6 kilo. So 3. So 20 divided by 6, you got 3.333 into 10 cube. So totally these are the stations count. 3333. Okay, 3,333 stations can simultaneously broadcast without interfering. Okay, so this is the another type of problem in AM. Okay, and another one, a 250 carrier, a 250 watt carrier of 1000 kHz is simultaneously modulated by sensor signals of 2 kilo, 6 kilo and 8 kHz with the modulation indices of 35%, 55% and 75% respectively. What are the frequencies present in the modulated wave and what is the radiated power? and what is the radiated power. Okay, so by given data, PC is given as a 250 watt. Why? Here they mention a 250 watt carrier. So that is carrier power PC, which is equal to FC 1000 kilohertz. Is nothing but 1 mega. So this carrier is used to simultaneously modulated by the sensor signal. So is nothing but the message signal. So 3 message signals is used here. First one is 2 kilo FM1. Second one is FM2 6 kilo. Third one is FM3 8 kilohertz. And the respective modulation indices mu1 is 35%. So 35 by 100 0.35. Second one 55%. 55 by 100 0.55. Third one 75% 0.75. Okay. So here the frequencies represent in the modulated wave. So first to take in the carrier. So carrier frequency is FC. FC is equal to 1000 kilohertz. This is nothing but 1 mega. Okay. So LSB1, lower sideband 1, that is equal to FC minus FM1. FC minus FM1. So first modulation signal taken. So this is the first two, and this one. Why? I am using 3 modulating signals or 3 message signals. So FC 1000 kilo minus FM1 2 kilo. So 998 kilohertz. And upper sideband 1. For the first message signal, upper sideband is FC plus FM1. So 1000 plus 2. So 1002 kilohertz. Like that, LSB2. LSB2 means LSB for the second message signal. FC minus FM2, which is equal to 1000 minus 6. It is 994 kilohertz. And USB2, upper sideband 2. That is FC plus FM2. So 1000 plus 6. So 1006 kilohertz. And again third message signal, LSB3, FC minus FM3. So 1000 minus 8. Why? My third message signal frequency is 8 kilohertz. So 1000 minus 8. It gives 992. And again similarly upper sideband for the third message signal is 1008 kilohertz. Now the radiated power is, you know that formula already we seen in previous problems also. PD is equal to PC into 1 plus mu square by 2. So these are the modulation index. So here we go to find mu of t is equal to mu1, mu2, mu3. Why? I am using 3 message signals. So 3 message modulation indexes. So 3 modulation index I use it. That is 0.35, 0.55, 0.75. Why? 35%, 55%, 75%. So I am required the total modulation index. So the total modulation index is mu t, which is equal to this formula. So when you solve this one, you get mu t is equal to 0.9937. Okay. So in this way you go to solve these problems. Okay. And next one, the incoming signal has a midband frequency that may lie in the range of 670 to 1790 kHz. The associated bandwidth is 10 kHz. So this signal is to be translated to a fixed frequency band centered at 540 kHz. Determine the tuning range that must be provided by the local oscillator. So here we are going to find the tuning range. of that local oscillator. So the given Fs, this is the frequency, or Fs signal frequency simply, is equal to 670 to 790 1790 kilohertz, 670 to 1790 kilohertz, and they given the bandwidth 10 kilohertz, and frequency, fixed frequency, that is it taken as a carrier frequency 540 kilohertz. Okay, so we know the formula F equal to Fs minus F naught. Here F naught is the local oscillator tuning frequency range. F naught is equal to 540. Why Fc equal to 540? Here the given Fc carrier frequency equal to 540 kilohertz, but the formula is Fc equal to Fs minus F naught. So I required F naught, then it is Fs minus Fc. Okay. So when Fs equal to 670 kilohertz, my frequency range of the local oscillator is 130. Why? F naught equal to Fs minus Fc. So Fs is 670, the given, minus F naught Fc. So Fs minus Fc, then I got 130 kilohertz. And again when Fs is equal to 1790 kilohertz, that equal to F naught is equal to 1790 minus 540. So totally 1250 kilohertz. So the tuning range of the local oscillator frequency F naught is 130 to 1250 kilohertz. So the given here. Okay, so this is the tuning range. Okay, and again you go to find some problem which is with the DSB. Okay, so an audio frequency signal M of t, which is equal to 20 cos 8 pi 10 cube t, is used to generate DSB for carrier of C of t. Here 20 cos 2 pi into 10 power 6 t. Calculate modulation, efficiency, sideband frequencies, bandwidth required, total power when R equal to 1. That means the resistor value is given as 1 here. So that is simply R equal to 1. So the modulation index formula is mu equal to AM by AC. Simply you can find without giving. So both having a 20. So AM cos 2 pi FMT. So that is a standard equation to represent M of t. And again the standard equation C of t equal to AC cos 2 pi FCT. So by using those two, you get to find the modulation index is 1. So 1 means modulation index 1 is perfect modulation. Okay. So efficiency is represented as eta, that is equal to PSB by PT is equal to 1. So PSB is the sideband power divided by total power is equal to 1. Okay. So PSB, which is equal to AC square AM square by 4R, that is sideband power, and total power is also same, AC square into AM square by 4R. So that's why the efficiency is 1. Now the sideband frequencies. The sideband frequency is upper sideband. We know that FC plus FM, and lower sideband we know that FC minus FM. So we can substitute FC value and FM value. You get 1.004 megahertz, that is upper sideband, whereas lower sideband is FC minus FM. So we got 99.006 megahertz, and the bandwidth required is nothing but 2 FM. So FM is given 4 kilo. So finally you get 8 kilo. And total power, that is PD is equal to AC square into AM square by 4R. So AC value is given as 400 and AM value is the same 400. Why? 20 square, 20 square. So AC value is 20 volts. So 20 into 20, 400. So 400 divided by 4. So totally got 40 kilowatt. Okay. So another problem is an audio signal frequency m of t is equal to 10 sine 2 pi 500t is used to ambient modulate a carrier of c of t is equal to 50 sine 2 pi to the power of 5t. Calculate modulation index, sideband frequencies, bandwidth requires, and total power delivered to the 600 ohms. So this is also same. What is the previous one? So we go to find the sideband frequencies, FC, FM. Okay, and again we are going to find the total power. The same formula, V equal to PC. So this is another problem which are having with the different values. Okay, so references here taken as from Sama Hakun and different textbooks like digital communications. Okay, so these are the different types of problems in AM systems. So in the next coming sessions we are dealing with the DSB and SSB. Okay, like that. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.